Okay, right now we're talking about the volume of a solid. We're trying to figure out the volume of a solid by using the integral. This is one of the important facts that we should learn in Cal 1, because if you know how to find the volume, then you know how to do other stuff in 3 dimensions. And we have many proofs that involve this too. So right now I have this function. Y is x squared, or we can say fx is x squared. And the range from this function is x from 0 to x to the 1. So what happens if we want to calculate the volume? What happens if we want to calculate the volume that formed by, we use this function and this area of the function, we rotate it around x-axis. So we rotate it around x-axis. And what that might look like is we rotate it, if you can visualizing it, rotate from x-axis. You will pretty much have something, let's see, you have something like this. Let's see if I can draw it. So it's like this. You have something like this. You have an open circle and things are going down that way. And inside of it is solid. The volume inside of this is solid. And how do we calculate the volume of it? First, you're visualizing how the solid looks like. Then you will realize that if you rotate around anything, they just stack with circles. So if we take one piece of this solid, let's say we take one small piece right here, and the piece has a volume pi r squared. Pi r, let's say the radius is r. Pi r squared times its height, and the height in this case is dx. So to visualizing this thing, we have a small cylinder that's infinite, and the height of the cylinder is dx, and the area is pi, and the area is pi r squared with the radius pi. You can see this. So this is actually one piece that we cut out from the solid. So how many pieces do we have in here? We have infinite number of the piece of this dx. We have infinite number of it from x is 0 to x is 1. Because according to the graph there, it's x to the 0, f to the 1, x to the 1. You just turn the shape vertically. So if we have this, what is the radius? We want to calculate the volume of one piece first. Then we're doing the definite integral of 0 to 1 according to the Riemann sum. If you don't know what Riemann sum is, go study Riemann sum first. Maybe we'll have another integration about what Riemann sum is. But a short description is Riemann sum is you have an infinite number of this small piece that's stacked together, and you add it together. That's the exact volume, or almost exact volume, with a different limit to the 0. The volume of this shape. So right here, which leads us to the integral from 0 to 1, because it's a Riemann sum from 0 to 1, and times the volume of one piece. What's the volume of one piece? Volume of the one piece is just pi r squared times dx. Why we know that? Because it's the area of the circle times the depth, and the depth is dx at this moment. So what we want to say is pi r squared times dx. And this basically just the volume of this depth. From 0 to 1 we have an infinity depth. And how do we do this? First we separate the constant. Pi is a constant. from 0 to 1. And we have r squared dx. And according to the four-dimensional theorem of calculus, taking the integral from something that relates to dx is just what? I mean, let's not call it this dx because it might confusing people. Let's call this dr instead. I'll just switch the dx to dr. Dx, dr, same thing, but it's easier to what? Because right now the radius is radius instead x. So we change everything to dr. So an integral of something to its expanded derivative is just its antiderivative. So what's antiderivative of this concept? It's just going to be pi times, because pi is a constant, we don't change it around if we take the antiderivative of it. What's the antiderivative of r squared? It's going to be r3 over, what's it? R3 over r3. The r is get off with the antiderivative, so this is basically pi squared, pi times r3 over 3 from 0 to 1. And from this now we can just calculate the value of formula. It's just going to be pi r3 divided by 3. And why is that important? Because this is a coin. And the formula of the coin is actually 1/3 pi r3. If a coin value circle, it means just this shape right there. I don't know what the shape's called, but it's that. And why is it important of that lesson? Let's say we don't have anything. We don't know what this is, what that is. And the radius, what's the radius? From there, we know the radius is fx. So let's erase all of that. Where's the eraser? Okay, right here. Let's replace all of that. Says we don't know anything, we don't know what shape this is, we don't know anything about that. Only thing we know is we're cutting a piece, and this function right here, from the middle of the shape to the bottom, every single radius, it's y to o f to the x, right? Because if you look at there, that's f to the x. So we switch it around, this is f to the x. So we actually just rotate the shape 90 degrees to see a view. So this is f of x. So the radius is f of x. And in this point, it's expand of dx. So this is expand of dx. So we're saying that depth is dx. f of x dx. And same thing, what's the formula? It's pi r squared. What's r in this case? R in this case is just f of x. So we have the integral from 0 to 1 pi times r squared, which is f of x squared, times the depth, dx. And this is our integral formula for one of the, let's say it's for one of the shape right there. But this is only applied when you're cutting the pieces, and when the pieces is a cylinder. And just plugging anything in it, then we got a volume of it. But what happened if we have a different shape? What happens is we rotate what? Actually, everything we rotated is just gonna be a circle, because when you rotate anything, it's gonna be a circle basis. That's how rotation works. You rotate 360 degrees, it's gonna be 360 degrees. And it doesn't matter, because if that point over there is from, let's say this point is from A to B, we're just gonna change the thing from A to B, pi times f of x squared dx. I don't want you to memorize this formula, but this formula applies all the time if they ask you for rotation. But all I want you to know is, if they ask for any shape, say they ask for a cube. They ask you for a cube. And they will ask you how to find the formula of the cube. It's simple enough. The volume of the cube. If you cut one piece out there, a smaller piece, it's just going to be the same area with a depth. And this depth is infinitely small. We assume we're not able to visualizing with our eyes. It's the depth of dx. And what is the length of dx is the size of the cube. And you know a cube is formed by squares, so the area times dx is just going to be x squared times dx. And if we want to do infinite number of this piece right here, say this is 0, this is some number, so this is a, this is b. From a to b, we're just doing a to b x squared times dx. So if it's a square, then it's x squared. If it's a circle base, then it's a pi r squared. So what is this exactly? So we can simplify the form. These two is the same thing, but just apply to different formula, but we all times the depth, which is dx. And we can apply it as the integral from a to b. The area of the shape times dx. Which means you have a shape, you have a solid, and you cut it to infinity number of the shape of the same, not the same, but the similar area. And each of the area from A to B, they sum out together, they add on together. That total thing is the volume of the shape. You can apply this to many areas of a solid if you want to, but that is our intuition today.